At 7:34 inches the morning, a drone sweeping over Mount Etna's upper southeast flank captured a site that should not exist, an unexpected 100-foot fracture tearing across the mountain's surface at 10,000 feet, a jagged wound that was not there the previous night. In the cool light of dawn, the camera reveals a raw, violently fresh scar, nearly 30 meters long, opening up to 7 meters wide, its edges sharp, unweathered, and clean of dust or moss. The ground is visibly offset centimeters in some places, nearly a meter in others, as if the mountain has been split along a hidden seam. The coordinates pin the rupture directly above Etna's most notorious sliding zone, the same prehistoric fault line where a 7,200-year-old flank collapse once sent millions of tons of rock crashing into the Ionian Sea, generating a tsunami that erased ancient coastlines. From the drone's vantage point, the geometry is unmistakable. This is not a superficial crack from routine activity, but a structural tear aligned perfectly with the ancient slip plane mapped by geologists for decades. As field sensors nearby spike with abrupt shifts in ground tilt, pressure, and microquakes, the first voices on the emergency channel speak with a tension that breaks the morning calm. Dr. Carmelo Ferlito, standing just outside the exclusion line, says the words no volcanologist ever wants to utter. This isn't just another scar. This is the nightmare scenario, exactly what every simulation warned about. And in that instant, the realization settles in. Etna did not simply crack. It has ripped open along the only line where it must never fail, awakening a disaster script written thousands of years ago, and hinting that history's most catastrophic volcanic collapse may be preparing to repeat itself. For thousands of years, Mount Etna has followed a set of geological rules so stable, so well understood, that entire hazard maps, evacuation plans, and scientific models have been built upon them. The volcano is one of the most active on Earth, a giant that erupts in some form during 8 out of every 10 years. Yet its behavior, chaotic as it seems, resides within long-established boundaries. Etna's southeastern flank has always been the restless one, creeping slowly downslope toward the Ionian Sea at rates measured in millimeters to a few centimeters per year, a motion driven by gravity, magma pressure, and deep structural weaknesses. This is normal. This is expected. Beneath the mountain, a multi-layered plumbing system stretches upward from a reservoir nearly 11 kilometers below the surface, feeding magma through a network of chambers where familiar minerals olivine, clinopyroxene, plagioclase crystallize in well-documented patterns. Even Etna's most violent paroxysms typically fall within the limits of historical behavior. For centuries, the southeast flank has slipped in slow motion, never as a single rigid mass, never along the full prehistoric fault plane that once unleashed a collapse so massive it triggered a 20-25-meter tsunami across the Mediterranean. According to nature's rules, flank collapses of that scale belong to geological time millennia, not years or decades. They require conditions far beyond ordinary deformation, rapid ground acceleration, meter-scale offsets, widespread slip alignment, and surface ruptures that match the deep geometry of ancient failures. Those scenarios exist only in textbooks, simulations, and paleo-tsunami deposits scattered across Sicily, Malta, and southern Italy. Yet today, those same rules are breaking. The fracture discovered at 10,000 feet is not where minor creeps occur. It is precisely on the ancient slip plane, carved with the same orientation and direction as the 7,200-year-old collapse. And instead of drifting at millimeters per year, instruments are detecting movements measured in centimeters, even decimeters, across days and weeks. Every model that predicted stability is now contradicted by the mountain's behavior. If nature has followed these boundaries for millennia, the question becomes unavoidable. Why is it choosing this moment to break them? At 2:14 a.m., long before the drone revealed Etna's gaping wound, 3 independent sensors registered a sudden, unnatural disturbance, an abrupt jump in ground tilt, a spike in subsurface pressure, and a burst of microquakes clustered tightly along the mountain's southeastern flank. When the drone footage arrived hours later, those early warnings snapped into focus. The fracture was not a surface crack, but the exposed edge of a deep, accelerating failure. Within minutes of the rupture being confirmed, a torrent of data poured into the INGV command center. High-resolution LiDAR, flown by helicopter and scanning billions of data points per pass, mapped a vertical offset approaching 1.5 meters, far beyond the gentle undulations seen during routine deformation. Crack meters, bolted directly across the fissure, recorded stepwise jumps in aperture, some widening by more than 7 centimeters overnight. The readings aligned perfectly with the central segment of the break, where the displacement was greatest. Then the satellites weighed in. Sentinel-1 InSAR images, processed in near real time, revealed that over the last 6 months, the southeastern sector had surged seaward by 5 centimeters, with its acceleration traced exactly along the geometry of the new rupture. Ground-based GPS stations, including ETNA, PIDs, and MNT, confirmed the story, showing 2 to 3 centimeters of lateral motion and roughly 1 centimeter of subsidence in just 2 weeks, while the western flank remained completely stable. Every line of data pointed to the same truth. The southeast flank was no longer creeping. It was sliding as a single, unstable mass. Field teams sampling the rupture uncovered a thin, clay-rich gouge layer with a shockingly low shear strength, less than 10 megapascals, a geological weak point capable of acting like grease beneath a giant moving slab. When wet or pressurized, this gouge becomes dangerously lubricated, primed for runaway motion. Gas meters added yet another alarm. Levels of carbon dioxide and hydrogen sulfide spiked far above background, especially at the southern tip of the fracture where the gouge is thickest. This was not the pungent burst of volcanic degassing from an eruption. It was a silent seepage from disturbed hydrothermal pathways, the kind triggered when deep rock layers suddenly shift and new fractures open. As all these measurements converged, Professor Luca Bonforte delivered the verdict. Every instrument is telling us the same thing. The slip plane, the displacement, the accelerations, this matches the ancient failure direction perfectly. This is not noise. This is the mountain moving as one body. Meanwhile, tsunami simulations based on a potential 5 cubic kilometer collapse produced wave heights of 20 to 25 meters, validated by the same sediment layers that recorded the 7,200-year-old megatsunami. The models were not predictions, they were replicas of what the Earth had already done once before, and now the sensors showed that Etna was aligning itself, piece by piece, with that prehistoric script. Across the slopes of Mount Etna, life moves under a shadow most residents cannot yet see, but every scientist and emergency official feels tightening around them. In the towns scattered across the volcano's southeastern flank, Zaffarana, Milo, Trecastagni, Nicolosi, families wake to roadblocks, redirected hiking routes, and the distant chop of helicopter blades sweeping across the new fracture. For locals, Etna erupting is normal. Generations have lived with ash on balconies and lava glowing on the horizon. But this is different. This time, the mountain is not erupting, it is sliding. And that distinction carries consequences measured not in miles of lava, but in minutes of warning. At lower elevations, farmers tending vineyards and citrus groves notice the first signs. Hairline cracks across access roads, sudden jams in irrigation lines, the faint scent of sulfur carried on warm updrafts. These details feel disconnected until news spreads of the 100-foot rupture at 10,000 feet. Fear grows quietly. A collapse is not just an Etna event, it is a Mediterranean one. Inside the INGV monitoring center, scientists stare at screens filled with synchronized deformation fields, LiDAR meshes, and real-time crack meter feeds. Professor Luca Bonforte, normally composed, watches displacement vectors pulse outward exactly along the ancient slip plane, while Dr. Carmelo Ferlito studies gas logs showing deep hydrothermal disruption. Each new reading confirms what no textbook ever truly prepares you for: an unstable mountainside moving as a single mass toward the Ionian Sea. In a different wing of the command center, tsunami simulations loop endlessly, each frame showing a potential 20-25-meter wave, striking the Sicilian coastline in under 15 minutes if the flank gives way. The tension is suffocating because everyone understands the timeline. Once the collapse begins, the gap between detection and coastal impact is brutally short. Meanwhile, civil protection authorities attempt to rehearse the impossible. Evacuation drills held in recent years paint a grim picture. During the 2023 exercise, over 12,000 residents from 18 towns took more than 4 hours on average to reach designated safe zones. Highways SS-120 and SS-114 lifelines for coastal escape became paralyzed within minutes, hitting double their safe traffic capacity. The SP-12, a narrow mountain road critical for towns like Milo, experienced delays of up to 2 hours, a catastrophic bottleneck if a megatsunami were racing toward shore. Add to this the collapse simulations from 2024. 40% of participants stranded by landslides or blocked roads, maritime evacuation achieving less than 20% success, and cell networks failing within the first hour of demand overload. For the 3 million people living on or around Etna's slopes, the stakes are painfully clear. The mountain's fracture is not just a geological event, it is a countdown. Scientists watch the data tighten. Officials debate impossible decisions. Families go about their day, unaware that their safety depends on a warning that, if the flank collapses, may give them less time than it takes to drive to the nearest open road. In this fragile space between shifting rock and crowded coastlines, data is no longer academic, it is survival itself. Behind the closed doors of Sicily's Civil Protection Headquarters, the tension is no longer about data, it is about responsibility. The fracture is widening, the southeast flank is sliding faster than at any point in recorded history, and yet the institutions tasked with protecting 3 million people cannot agree on what the public should be told. Internal memos reveal the first battle line. The official threshold for raising Etna's alert level is 5 centimeters of movement per day, a benchmark designed decades ago for slow deformation, not for the accelerating slip now unfolding across the mountain. But GPS logs are already showing 7 to 7.2 centimeters per day, surpassing the trigger by nearly 50%. For INGV volcanologists, the implication is obvious. The threshold has been broken, and the alert must rise immediately. Their argument is simple. Hesitation could cost lives. Yet emergency planners push back. They remind officials of past evacuations, where even minor warnings triggered gridlock, panic, and hours-long bottlenecks on roads that buckle under ordinary tourist traffic. The SS-120, SS-114, and SP-12 routes, essential escape corridors, reach double their safe capacity in under 10 minutes during drills. If a premature alert sparks a mass self-evacuation, these choke points could turn thousands of cars into stationary targets along the very coastline. A collapse-generated tsunami would strike first. The planners' fear is not irrational. A megatsunami would hit Catania's port in as little as 15 minutes, long before any uncoordinated exodus could clear the danger zone. The conflict deepens as new leaks spread. A classified after-action review from the 2024 collapse simulation warns that 40% of residents would become stranded due to landslides and blocked routes, and that maritime evacuation would fail for most coastal towns. Another document admits that cell networks collapsed within an hour during testing, leaving command centers blind to the status of entire neighborhoods. Scientists argue that these findings only reinforce the urgency of raising the alert. Officials counter that announcing the full extent of the risk may create a disaster before the volcano does. Within the crisis rooms, the debate turns philosophical. Should authorities warn the public early and risk paralysis, or stay silent a little longer, hoping for more clarity but gambling with millions of lives should the flank collapse without warning? One exhausted official voices what no policy document dares to state. If the flank goes, no warning will be enough time. It is a statement that hangs over the room like an aftershock, splitting the factions even further. But the volcano is indifferent to human disagreements. The fracture continues to widen. The gouge layer grows wetter and weaker. Gas emissions climb. Tsunami simulations flash red. While scientists and policymakers struggle to control the narrative, Etna controls the timeline, and the Earth does not wait for consensus. Across the Mediterranean, a new map of danger is beginning to take shape, one drawn not by politics or borders, but by the physics of collapsing mountains and the brutal speed of tsunami waves. Mount Etna's southeastern flank is no longer behaving like a restless slope. It is behaving like a system entering the final stages of structural failure. And in a region where millions live within minutes of the coast, that shift changes everything. Zooming out from Sicily, scientists are starting to connect Etna's instability with a wider pattern of flank collapses observed across volcanic systems around the world. While Etna has erupted for 3,500 years with relentless regularity, the mechanism now unfolding a deep-seated slip along a prehistoric failure plane belongs to a far rarer class of disasters. These are events capable of displacing tens of cubic kilometers of rock in a single catastrophic movement, generating waves that radiate across entire basins. The deposit layers found in Sicily, Malta, and southern Italy, marked by coarse sands, gravel, and volcanic ash, are the geological echoes of the last time Etna unleashed such devastation 7,200 years ago. Now, satellite displacement fields and LiDAR scans are sketching out the same geometric alignment, point for point. But this new reality is not defined by Etna alone. It is defined by the collision between natural timescales and human density. The Mediterranean today is not the ancient world. It is a tightly connected corridor of coastal cities, ports, airports, and industrial hubs. A 20-25-meter wave hitting Catania, Malta, or the Italian and Greek coastlines would no longer erase villages. It would cripple modern infrastructure, overwhelm evacuation capacities, and send shockwaves through global shipping and aviation networks. That is why the simulations reviewed by Dr. Georgios Papadopoulos feel less like academic exercises and more like previews of a disaster whose consequences would ripple far beyond Sicily. In this emerging era, the stability of volcanic flanks is becoming as critical as eruption forecasting. Traditional models, built for lava flow, ash plumes, and summit explosions, were never designed to handle the speed at which flank collapses can unfold. A megatsunami does not allow for negotiation. It offers a warning measured in minutes, not hours. And as Etna's fracture widens, its gouge layer weakens, and its deep plumbing shifts, scientists face a truth too heavy to ignore. This is the first time in human history we are watching such a collapse form in real time, with instruments sensitive enough to capture every millimeter of motion. What follows from here is not just a question of geology, it is a question of readiness. The mountain has already chosen its trajectory. The sensors are recording it. The simulations are validating it. The only uncertainty that remains belongs to us. If this is the beginning, imagine what comes next.